explanation. All right. So what I'll do, I'll mark the current directions. Okay. AC current directions I'm marking. Say this is IB, IC, and this is your IE. Okay. Remember one thing. In case of emitter follower circuit, the current direction IE and the two-port standard current direction, okay, I naught will be in the same direction, right? This is how the current is going to enter, okay, and it cannot get into the transistor network because this capacitor will be the low resistance path and it will flow through the load terminal. Okay, so this is how your I naught is going to flow. Okay, so if you compare the direction of I naught with IE, you can clearly observe that they are in the same direction. That's the reason the polarity of V naught will not change. So V naught will have the designated polarity. Okay, whereas in case of an amplifier circuit wherein you take the output from collector to ground, always there used to be difference in polarity convention, right? Okay. So this is one of the feature of emitter follower, that I naught and IE direction are the same. Okay, therefore V naught can be given as I naught into RE, or it is as good as IE into RE. Okay, so this is the observation which holds good for an emitter follower circuit. Okay, right. So that being said, let me tell you some features about emitter follower. Okay, before taking up the analysis features. So first feature, as I have told you, that the voltage gain approximately remains 1. That means to say V naught and Vi are in phase and identical, you can say. Identical. Okay. The second feature is that your emitter follower circuit gives input impedance, okay, in the moderate range. Moderate range as in terms of few kilos of ohms to several hundreds of ohms. Okay, you can say up to few kilo ohms. Okay, say typically less than 2 kilo ohm. Okay, on the other hand, Z naught is very low, up to few tens of ohms. Okay, say typically less than say 100 ohms. Okay, so this is the feature, and because of this feature, it is widely selected in impedance matching. Impedance matching, okay, because of low Z naught, right? If your speaker impedance is about 32 ohms, you can compare the output impedance of emitter follower, very close to that of the speaker impedance, right? 100 ohm is close to 32 ohms of speaker impedance. Okay, so these are the major features. Okay, they may ask for short notes. Okay, fine. Now let us take up the analysis. Okay, so to do the analysis, what is that we should do first? We should obtain the RE model. So first let us find RE model. Okay, so let's do the RE model. Okay, I'm going to replace the transistor with the RE model. So this is my base. So I will have beta RE here, and on the collector side I'm going to have beta IB. Okay, So this is my collector terminal. Okay. And this is then connected to emitter terminal E. Okay. As you can clearly observe that, there is no short circuit taking place across the emitter terminal. So emitter resistor RE is retained in the circuit. Okay. So let us retain RE and let us short circuit the capacitor. Let me start from output capacitor. So this will be replaced with a short circuit equivalent. Okay. So what you have is, this is RE. What I'll do, I will just write this emitter on the other side. Okay. So this is what I have done. Okay, and this is where I observe my output. Okay, from the emitter terminal to ground terminal, minus, plus. Okay, so that will be on the output side. And the collector terminal, okay, what will happen to collector terminal? Can anyone tell me? So this collector terminal is directly connected to VCC, and for AC analysis, VCC is grounded. So it is something like, collector is held at ground potential. So this collector terminal is simply connected to ground. Okay, bring way down and just connect it to ground. Okay, and on the input side, you have the base resistor RB. Okay, the other end of RB is connected to VCC. For AC analysis, VCC is grounded, so the second terminal of RB is also grounded. Okay, and then you will have your input coupling capacitor, which is short circuited, and finally you will have your input voltage VI. Okay, so this is your RE model. Okay, once the RE model is done, what you can do is you can mark the various transistor currents. This is IB, this is IC, okay, and this is IE, and in the same direction, I naught flows. Okay, so these are the various transistor currents. Okay, what I will do over here itself, let me write IE as 1 plus beta times IB, because I have a ready-made expression which will help me in replacing IE in terms of IB. So I have directly substituted IE as 1 plus beta times IB. All right. So yeah, and then you will have to mark the standard 2-port network current II. Okay, this is IB, and this, let's say, some unknown current IX, which is of no good use, but we will mark, okay, something like IX amperes. All right then, so this is our RE model for emitter follower. Okay, any doubts?
No, sir.
So now let's look at ZI. Okay, so ZI is taken as VI by II. Okay, now I think few of you must have observed, okay, that your input impedance is not the simple, parallel combination of RB and these two resistors, right? Because through beta RE, current IB flows, and through RE, current IE flows. So you cannot simply say that across base and ground, you have a parallel combination of RB with a series connection of beta RE and RE, provided you somehow adjust your circuit analysis in such a way that through beta RE and RE, the same current flows. Okay, that's the reason, beforehand only, I have replaced my emitter current IE with 1 plus beta times IB. Okay, so to find ZI, okay, it is similar to your unbypassed capacitor case. What we will do is we will take this input voltage VI right across base and ground terminal. Okay, so let me place VI, okay, over here itself. Okay, and then let me write the input voltage VI as, okay, VI as, okay, what is VI? VI is equal to current into resistance. So basically it is IB into beta RE, IB into beta RE plus IE into capital RE. Okay, and we know that IE is 1 plus beta times IB. So what you can do is IB into beta RE plus 1 plus beta times IB into capital RE, and you take out, you know, IB outside the bracket, so you would get VI is equal to IB times beta RE plus 1 plus beta times capital RE, or you take out the ratio voltage by current. Okay, and let us define this ratio as some impedance ZB. Okay, so ZB simply gives the impedance as seen from base terminal. Okay, it is not the impedance seen from the input terminal. Okay, so this is ZI for us. Okay, and this is ZB for us. Okay, so ZB is as seen from base terminal and ZI is as seen from the input terminal. All right, so that gives basically a series combination of two resistors, beta RE and 1 plus beta times capital RE. Okay, so once ZB is found, you know, you can say that the overall input impedance ZI is the parallel combination of RB and ZB. Okay, so this is my VI, this is my II, okay, and this is what I am interested in, right? ZI. So ZI going to be the parallel combination of RB and ZB. Okay, so that's my input impedance. Okay, fine. So we have found the input impedance. Now let us find the output impedance. All right, Z0. So by definition, you know, Z0 is V0 by I0. Okay. Now, if you look at the output circuit is again not straightforward, right? You have a current source and you have emitter resistor, and this emitter resistor is common to the input circuit as well as the output circuit. Okay, so there is some level of you know, complexity in the circuit. So whenever there is complexity, the way to come out of this complexity is the application of network theorem. Okay, so what we will do is let us apply Thevenin's theorem to find out the Z0. Okay, so let us apply Thevenin's theorem. Okay, because the circuit is having more than one source, right? You have a current source and you also have an voltage source on the input side. So let's apply Thevenin's theorem. Okay, so as per the Thevenin's theorem, what we will do is let us short circuit VI and open circuit beta IB. Okay, so this beta IB is current source for us, independent, dependent current source, and VI is you know, independent voltage source. Okay, so let's do that. So when we do that, what will happen is, okay, so we will have a short circuit across VI position. Okay, this is where your VI was existing previously. Okay, and what we have next, we have the base terminal, and between base and ground you have had a base resistor, right, RB. Okay, and then you have had your beta RE and the emitter terminal and the emitter resistor. Okay. Okay, and this is where you are interested in to find out the Z0. Okay, Yeah, so that's my circuit. Okay, if you ask me what will happen to the collector terminal, okay, so current source is open circuited, right? So there will be an open circuit across the collector side. Here it is, here. So this current source is open circuit, and hence you will have a loose wire over here, which is of no good use, right? So you see here, there is a loose wire here, which is meaningless to keep in our circuit. So what I will do, if you want, you retain it, or if you want, you just neglect it. Okay, it's okay. I'm not going to delete it. I'm just going to neglect it. It's a loose wire. It is of no good use because there's no resistor coming into picture. All right, fine. Now you start observing from the left hand side. Okay, you see here between base and ground, you have base resistor RB, right, on one side. On the other side, if you see between base and ground, you have a short circuit. So what happens is that this short circuit, okay, this short circuit, okay, let me write this as short circuit. So this short circuit will short circuit the resistor RB as well, right? Because see, between base and ground, you have a straight conductor. Okay, so obviously RB is going to get short circuited. So that means to say, what I can write is base is at ground potential, right? So base is at ground potential. Okay, and this is due to, okay, let me write inside the bracket, due to the short circuit created by Vi, right? So Vi basically creates the short circuit, and due to which base is held at ground potential. Okay, now let me redraw the circuit. So what I'm going to do, I'm going to eliminate resistor RB because RB is getting short circuited, right? So what I will do is, let me create the short circuit here. Okay, and this is my base terminal, and then I'll have my beta re here. Okay, and I will also be having my emitter terminal here. Okay, and this is my RE. Okay, so this is what the circuit looks like. Okay, after reduction. Now what we have to do, we have to mark the currents. So through beta RE, IB flows, right? And through RE, IE flows. Okay, so what I will do, let me rewrite this current IE with 1 plus beta times IB. Okay, 1 plus beta times IB. So by doing that, what I will get is a parallel combination of beta RE. You see here, the other end of beta RE is grounded. Let me ground it. Okay. So this is basically my base terminal. All right. And let me take this as the emitter terminal. Okay. Emitter terminal is here. To this emitter terminal, what is connected? RE is connected. Okay. RE is connected. And that RE, we shall take it as 1 plus beta. Okay, that is RE times 1 plus beta, simply because we are trying to, replace this RE with the same entity as IB. Okay, and the other end of RE is also grounded. Okay, and this is where I will be seeing my output impedance. Okay, now what do you see from the output side? So when you look into the circuit from the output side, you will see that a parallel combination of beta RE and 1 plus beta times RE. So your output impedance Z0 is basically the parallel combination of beta RE with 1 plus beta times RE. Okay, so approximately you can say it as beta RE parallel with beta RE, the capital beta RE. Okay. So Z0 can be written as beta RE into capital beta RE divided by beta RE plus capital RE into beta. Okay. Or you take out beta common. So what will happen is, beta RE. Okay, so this is beta square into small r into capital RE divided by beta times small re plus capital RE. So basically, one beta gets cancelled. So approximate expression for Z0 going to be product of effective resistance and the biasing resistance divided by summation of the two resistances. So that's your Z0, right? So that is your Z0. Fine. Is it clear?
Sir, what about one more beta, sir? One beta is there, no, sir?
Which one? This one is it?
Yes, sir.
Yes,
This
sir.
is in the numerator.
Yeah. See, which one? Oh, I'm sorry.
You cancelled, no, sir?
Yeah, I mean, it is beta square, right? So this one beta is remaining here. Correct? No?
Yes, sir.
Yeah, one beta. Because beta into beta was taken as beta square, and the two, I mean, one beta was cancelled with the numerator, I mean, denominator beta. Yeah, correct. You are right. So this one beta left. Okay. So that is what our Z0 expression is. Okay. Next, we have the voltage gain. Okay. So AV is V0 by VI, where V0 is equal to, you can say that output current into output voltage. Okay. So it is I0 into RE, okay, which is also equal to IE into RE, because I0 is equal to IE for emitter follower circuit, or you can write V0 is equal to IE. So IE we can write 1 plus beta times IV into RE. Okay. So let us take this as our voltage expression. Okay. Fine. So what we will do is, we will try to substitute IB, okay, from the input expression. Okay. So you can say that where IB is equal to, okay. Now from where we can substitute IB, okay. You have seen already the input impedance, right? Yeah, here it is. See this expression. This expression. So IB can be substituted as VI divided by ZB basically, right? So let me write it here, where IB is equal to, in bracket let me write from equation start. Okay, so where IB is equal to voltage divided by impedance. Okay, so let us substitute. Therefore, V0 is equal to 1 plus beta into IB, right? In place of IB, what do we have? VI divided by ZB we have into capital RE, which is equal to 1 plus beta into VI divided by ZB. What is ZB? ZB is beta RE plus 1 plus beta times capital RE. So for simplicity, what I will do, I will write beta times RE. Okay. What I have done, 1 plus beta I have written as beta itself into RE. Okay. So what you can do, you can bring this VI onto the left hand side so that you will get the ratio V0 by VI, and that ratio we can take it as AV. So V0 by VI is equal to the right hand side terms. You have 1 plus beta into RE on the numerator, and on the denominator you have beta times Re plus capital Re. Okay, once again, this 1 plus beta, we can take it as beta. So it is beta times capital Re divided by beta times the ratio Re plus capital R. So this beta gets cancelled. So what you get is the voltage gain expression, something like AV approximately equal to Re divided by Re plus Re. Okay, so this is our voltage gain expression. Now, if you observe carefully, in the numerator you have Re, and in the denominator you have Re plus Re. Okay, where Re is very small, right? And what's the range for this small Re? Few tens of ohms. That's all. 15 ohm, 20 ohm. That's all. Okay, so that's the reason. If you observe carefully, you would get a avenue. Okay, something like your denominator is slightly larger than the numerator. That is the reason your AV is very close to unity. Okay, it may not be unity. That is because denominator is slightly bigger than the numerator. But practically you will get a value something like 0.928, 0.98, etc., etc. Okay, it's very close to unity. So that's your voltage gain. Okay, and current gain AI. Okay, as usual, AI is equal to I naught by II. Okay, so that will give you AV times Zi by Z naught. Okay. Okay, that's your current gain, the normal expression. Okay, so that is your emitter bias analysis. Okay, very important emitter bias analysis. Okay, so it is close to your unbypassed capacitor case. Okay, only the difference is that there is no amplification taking place. Okay, fine. Any doubts? Any doubts?
No, sir.
Okay. So let's consider few problems, okay, on emitter bias. Okay, wait, I did not solve any problems from this one, collector to base bias, right? Fine. So write down, for a collector to base bias amplifier, okay, it is not common base, so let me write collector to base amplifier. VCC is 9 volts. RF is 180 kilo ohms. RC is 2.7 kilo ohms. Beta is 200. Beta is 200. Yeah, that's all. So determine RE, ZI, Z0, AV. Determine RE, ZI, Z0, AV. Okay. So collector to base bias. Which circuit is this? Collector to base bias. Collector to base bias is this circuit. Okay, this circuit. The previous class we did, right? This is the circuit. So for this configuration, this one, collector feedback, okay, or collector to base bias. For this configuration, RC value is given, RF value is given, and RE is not given. That means to say RE is getting bypassed. Okay, that is what you have to understand over here. And you have been asked to find out effective resistance RE, ZI, Z0, and EV. Okay, so what you have to do is you have to go back to the collector feedback or collector to base bias amplifier, and you have to collect the results from there. Okay, fine. So first of all, what we need to find out? We need to find out RE. So RE is 26 millivolt divided by capital IE. Okay, so IE is 1 plus beta times IB. That implies IB for a collector to base bias is VCC minus VBE. Okay. Okay, let me quickly draw the circuit so that you know you will be able to compare. This is RC. This is your RF. Okay. This is VCC, and okay, here they haven't given RE value. So RE is resting at ground potential. Okay, directly they have connected this emitter to ground. Okay. This is VI, CI, C0, V0. So this is the circuit. So RC is given 2.7, RF is given 180, beta is given. That's all we need. So find out IE. So since there is no emitter resistance, so your IE going to be VCC minus VBE divided by RF plus 1 plus beta times RC. Okay. If RE was present, you would have had within the parenthesis RC plus RE, right? This is our usual expression, but RE is not present. That means to say, you know, emitter is directly held at ground potential. Just substitute RE with 0. That's the reason, you know, in the denominator, you are left with 1 plus beta times RE. Okay, so what do you get IB as? So IB is equal to VCC 9 volts minus VBE, assuming silicon transistor, divided by RF, that's 180K plus 201 times the collector resistance. Okay. So quickly calculate and tell me the answer. Is it 11.48 microamperes? So 11.48 microamperes. So that's your IB. So therefore, IE becomes 1 plus beta times IB. Okay. So that's 201 times 11.48 microamperes. That's 2.308 milliamperes. Okay. So once IE is determined, you can find out the effective AC resistance RE, 26 millivolt divided by 2.308 milliamperes. milli gets cancelled. So 26, 11.26. Okay, so 11.26 ohm is your RE. So first part is calculated. Okay. Next, let us take up ZI. Okay. So ZI for collector to base amplifier. Okay, collector to base amplifier is ZI is equal to, okay, if you want, let me just show you. Here it is. Somewhere here we found ZI. Yeah, ZI is equal to RE divided by 1 plus beta plus RC by RF, right? So that's our ZI expression. So ZI is equal to RE divided by 1 by beta plus RC parallel with, sorry, RC divided by RF. So that is 11.26 divided by 1 by 200 plus 2.7K divided by 180K. So how much are you getting? ZI as
563
ohms. Perfect. So that's your ZI. So let us strike out ZI as well. Okay. Next, what we have is Z0. Okay. So for Z0, we directly obtain Z0 as RC. So RC is 2.7 kilo. So Z0 is RC. Let me show you in the previous analysis. See, RC parallel with RF, but you know, it is very small, so you can always say that Z0 is closer to RC itself. If you want, I can show you RC parallel with RF, right? You can just find out. It is 2.7K into RF. RF is 180K divided by 2.7K plus 180K. Okay. So that's 2.66 kilo. So this is what I was telling you. Very close to each other, 2.7 and 2.6K. It doesn't matter. Okay, either you take this expression or this expression. Okay, so that's your Z0. Okay. So even Z0 is found, and finally we have AV. Okay, so AV expression, okay, we obtain AV as here, right? Approximately AV is minus RC by RE. Okay, so let's go back. So minus 2.7K divided by RE, 11.26. So it's minus 239.78. Okay, so that's your collector to base bias circuit. Okay, so that's the solution for collector to base bias circuit. Okay. So second problem, let me take. For the circuit shown below, determine RE, ZI, Z0 and AV. So there's a capacitor and there's a ground terminal. Okay, I will disable these lines so that you'll be able to observe the circuit more clearly. So this is your input coupling capacitor. And this is V0, C0, Ci. This is 120 kilo ohm and this is 68 kilo ohm. Okay, collector, base and emitter. Okay, so they have given emitter at ground potential, right? So this is the circuit. So for this particular circuit, you need to determine RE, ZI, Z0 and AV. So how do you solve? So to solve this, first you have to construct RE model. Okay. So first let me substitute the RE model for CE configuration. Beta RE and grounded because emitter is directly grounded. Then I have the controlled source on the output side, beta times IB. Okay, where IB is the current flow through beta RE resistor. This is my collector and this is my base. Okay, fine. I want you to observe one important thing. Now, for DC analysis, what will happen to this capacitor? For DC analysis, this capacitor, okay, let me call that capacitor as some CM. Okay, CM. I'm just giving a name. So let me write here. For DC analysis, CM is open circuit. OC means open circuit. This is for DC analysis. On the other hand, for AC analysis, CM is short circuit. Now we are constructing RE model. RE model is AC analysis. So what you have to do is you have to replace this central capacitor with a short circuit. So this is a short circuit. This is a short circuit. Okay. So the capacitor is replaced with a short circuit. So, there exists a central ground connection. So that means to say 120 kilo ohm resistor is connected. Okay. It is getting connected between base and ground, G for ground. And this 68 kilo ohm resistor is getting connected between collector and ground. So this is coming in between collector and ground. So what we will do is we will place this 120 kilo ohm resistor between base and ground. So that is your 120 kilo ohm resistor. Similarly, on the output side, let us place 68 kilo ohm resistor between collector and ground. Okay, this is a very peculiar problem. Okay, that's all. And then, you will replace this capacitor Ci with a short circuit and you will connect your input. And similarly, on the output side, you will short circuit the output capacitor and you will observe your V0. Okay, so This is your I naught and this is the output polarity. That's all. That is the difference. Okay, rest all remains the same. So your Zi going to be 120 kilo ohm parallel with beta Re. Okay, and Z naught going to be 68 kilo ohm. Okay, and your Re going to be 26 millivolt divided by IE. Okay, where your DC current IE is 1 plus beta times IB, and IB is VCC minus VBE, okay, divided by RF plus 1 plus beta times RC. Okay, so once IB is known, you can find out IE. Once IE is known, you can find out RE. With RE, you can find out beta RE as well. Okay, so beta value is not given, right? So beta is 140. Okay, is given in the problem. Okay, so find out Zi value, Z naught value, and as well as the AV value. Okay, so AV is V naught by VI. So AV you will get it as minus okay, it is basically 68 kilo ohm divided by RE you will get. Okay, is there any RC? Oh yeah, RC is given. I have missed out. 3 kilo ohm. Okay, so sorry, RC is there. So this is where the RC comes into picture. 3 kilo. Okay, this is your RC. So Z naught is 68 kilo ohm parallel with 3 kilo ohm. Okay, 68 kilo ohm parallel with 3 kilo ohm. So this is how you solve this problem. Okay.